Everyone, so how's it going? Hopefully the exam wasn't too hard or anything like that. Haven't graded them yet. But this is it. We've kind of like done all of the beginning that we need to do. Um, and we're gonna just jump right into proofwriting. So I'll say at this point in the class, I'm still going to be following the slides mostly in that we're going to be doing the stuff in order and I'll do some examples from the slides. But then I am going to kind of veer off in like the labs and stuff to talk about more interesting things that we can do with proofwriting. We'll be talking about stuff with the prisoner's dilemma when we talk more about graph theory kind of stuff. We'll be doing stuff with the Fibonacci numbers when we talk about recursion. We're even going to do something called the Monty Hall problem, which is like a big problem in like probability. And the reason it's called the Monty Hall problem is because there's a game show that used to be on TV that the problem is based off of. We'll be doing some of that stuff. Proofs are weird when you first start doing them because they seem almost intuitive. And then like if I tell you 2 times any number is an even number. Okay, yeah, that's pretty intuitive, right? Like if I take every number and double it, I'll have an even number. That's fine. Or like an even number plus an even number is an even number. It's like, okay, sure. But how do we like prove it for all even numbers, no matter what? Okay, it'll seem very weird at first, but hopefully, just kind of through practice and getting used to writing in this abstract kind of way, it'll make sense. Today, we're gonna start with number theory. That's that's the easiest one to start with proofs, right? And that is like the 2 times an even number is an even number. That's really the very basics of number theory. So we're gonna start with that just so we're not getting confused in the concepts and the proofwriting. We're gonna focus on concepts we already know to be true, but we're going to have to start proving stuff. Okay, so the first thing we're going to need to talk about is there's really 2 kinds of proofs. Okay, so there's 2 kinds. Can you work? Thanks. 2 kinds of proofs. Okay. The first kind is called a direct proof. Okay, it's called a direct proof. And what a direct proof is you're given a bunch of assumptions and then you prove the conclusion, right? So given assumptions, you prove conclusion. This is, I will say, the most clean type of proof, okay? But that doesn't mean it's the best. You will find people out there that don't think if you prove something that's not a direct proof, they'll think that that's not a real proof. That's not true at all. And the other type of proof is a counterexample. Okay. Okay, and the counterexample proof or proof by contradiction. Okay, so I'll say proof by contradiction, which are slightly different. So actually, I'm gonna make that a third kind, proof by contradiction. If you've seen something called induction, that's technically a direct proof. So that's why we don't list it separately. But yeah, so a counterexample is when you're trying to disprove something. Okay, you just find one counterexample and the whole proof falls apart. So you've disproved it. Okay, a proof by contradiction is you say, well, assume that my assumptions are false. Let's see what happens. And so if I assume that my contradiction is false, and let's see what happens. And then you'll keep going through your proof, and then you'll get some kind of weird thing in your proof, like 2 = 0. That's a contradiction. So then you say, well, since I got a contradiction, if I assumed my conclusion was false, my conclusion must then be true. That's proof by contradiction. Okay, so let's keep going. I'm gonna say these are things that will be true for us. They are not always true. And if some of you are math majors, you will learn that this is not always true. Actually, yeah. Well, I'll just leave it at that. So a couple of things that we know to be true is if A equals B, that means that B is equal to A. Totally cool, right? Another one is that seems kind of obvious, but A equals A, so like 0 = 0. Okay. And then the third one is transitivity. So A equals B and B equals C. Well, that means that A equals C. Okay. So this is called transitivity, in case you're wondering. Transitivity. Okay. And I'll be doing little sidebars like this that kind of deviate from the notes, but that's okay. So these are things that we're going to have to know that we're just going to kind of always assume to be true. So it doesn't matter what side of the equal sign you write things on, right? If you have something, it's always equal to itself. And then if A equals B and B equals C, then A equals C, right? So we're going to have to assume these to always be true, right? The other thing that we're going to have to assume to be true is if A equals B, then we can substitute A and B however we want. So we can substitute if two objects are equal. Okay. And number 5, the last one is that two integers added together. Okay, so two integers added, subtracted, or multiplied together is an integer. Okay. So these are things we're going to take to be true. The last one's very weird, right? I mean, it's not weird because if you think about it, 1 + 2 is 3, and 3 is also an integer. But assuming number 5 seems kind of like you're assuming too much. But for those of you who have had linear algebra, the integers are something similar to a vector space. Okay, they're called a field. Okay, they're called a field. And they have axioms they have to follow, just like vector spaces do. And one of the rules of vector spaces is they have to be closed under addition and multiplication, right? So since integers kind of fall in that category, they're also closed under addition and multiplication. If you haven't had linear algebra, that probably didn't make sense to you, and it doesn't matter. So as long as we assume this to be true. Okay, so here are some useful definitions for us. Okay, and it's going to seem weird, right? But that's okay. So we'll say n is even if and only if n equals 2 times k for k an integer, right? So an even integer or an even number is 2 times some integer. That is the definition. Okay, there's no need to prove it because that's the definition. Okay, That's the first one. And the second one is n is odd, if and only if n equals 2k plus 1. Okay. 4k in the integers. So these are going to be our main tools. Okay. Even and odd. We're going to use one more, and that's prime numbers, but let's do some examples. Let's just make sure we're okay here. Okay. So example. Okay, is negative 301 odd? Is it odd? Well, let's see. Okay, in order to be odd, I need it to be 2k plus 1. Okay, so if I said, hey, k is equal to negative 150, then I have 2 times negative 150 plus 1. Well, look, that's negative 301. So it's in the odd form, right? So therefore it's an odd integer. Okay. What about if we do C? Okay, if you're following along on the slides. Okay. What if we do is 6a squared times b even? Now, I don't tell you what a and b are. They're integers, though. I don't tell you what they are, but they're just some integer. Well, let's think about how we write this. Okay. 6a squared b is the same thing as 2 times 3a squared b. And we know that 3a squared b is an integer. How do we know this is an integer? Well, we know it's an integer by our assumption 5, right? Where if you take any integers and multiply them together, you're going to get an integer out. So now we have 2 times some integer, let's call it k, right? If k is equal to 3a squared b, right? That's exactly what it means to be even. So it's even, okay? And that's the kind of manipulation we're going to try to do. Okay, we're going to look at things and be like, all right, is it 2 times something or is it 2 times something plus 1? How am I going to do this, okay? So that's even and odd. Let's talk about prime now. Okay, so here's some more definitions. Okay, the definition of prime is weird. Okay, so n is an integer. Okay, n is prime. Okay, if and only if, okay, if and only if n is greater than 1, so we're defining prime numbers, got to be greater than 1. And, okay, I'm going to write it in symbols, but we'll figure it out. Okay, for all R and S in the positive integers, okay, if n equals rs, so r times s, then r equals 1 and s equals n, or r equals n and s equals 1. Okay, so this is the formal definition of a prime number, right? With all of our fancy symbols and everything. So once again, let me repeat what this means. If we have some n in the integers, so some integer, and it's bigger than 1, then it's considered a prime number if I give you 2 numbers, r and s. Doesn't matter what they are. It has to work for all of them. And they have to be positive integers. If n is equal to r times s, the only way this will be true is if r equals 1 and s equals n, or r equals n and s is 1. Okay. In our terms, it's the same thing as saying the only two numbers that go into a prime number are 1 in itself, right? That's what this is saying, but this is saying it in symbols, okay? So we're gonna have to get used to looking at definitions this way. They're gonna keep kind of popping up this way, so we'll get used to it, it's okay. Okay, so that's what it means to be prime, okay? There's another word, maybe you haven't heard it before. It's called composite. Okay, so the other one, oops, is composite. It just means not prime. Okay, so if you have an integer, okay, n is composite. Okay, once again, we say n has to be greater than 1. Okay. N has to be greater than 1. And there exist some positive integers, r and s, such that if n equals rs, right? So if that's true, then 1 is less than r, less than n, and 1 is less than s, less than n. Okay, what does this mean? It means if I give you like the number 21, right? Then there are two positive integers between 1 and 21 that multiply to 21. But it has to be true for all numbers, right? So for 21, the answer is 3 and 7, right? So r could be 3, s could be 7. I found two integers, right? There exist, which means there's only got to be one pair, right? And our one pair for 21 is 3 and 7, right? To be composite, right? So composite just means not prime, really is what it means. Okay, so let's just make sure we're okay and we know some of our prime numbers. So the first 6 prime numbers, okay, so not 1. So 2 is 1, right? Because it's only 2 and 1. And then also 3 and 5 and 7 and 11 and 13. Okay. And then the first 6 composite numbers, okay, are going to be 4 and 6 and 8 and 10 and 12. Oh, and we forgot 9. And 9 and 10 and 12. Okay. Question for you, and just think about it, and then I'll kind of pause. Is every even number a composite number except for 2? Because we see 2 as a prime number. Is every other even number besides 2 a composite number? Right. Think about it for half a second. Okay, the answer is yes. Okay, because no matter what the even number is, right? You can think of one, I don't know, 108. 108 is an even number. Well, 2 times 54 is 108. So I can always find two numbers, 2 times something, right? That will give me whatever even number I just thought of. Okay. All right. So let's move on. So we're going to start trying to do some kind of proofs, okay? So the first thing we're going to do is we're going to talk about proving existential statements, okay? So this is proving These are your favorite things, proving existential statements. And why is that true? Well, if I say, you know, there exists some thing in my domain such that something happens, okay? All I have to do is I have to find one. I have to find one of them that works. There could be 10 million of them that work. I just have to tell you one, because then I showed there exists one, okay? So let's try it out. Okay, let's prove that there exists an even integer. Okay, prove that there exists an even integer, n, let's call it, that can be written two different ways. Okay, two different ways as the sum of two prime numbers. Okay, let's do this. Okay. So first off, right, I want to prove there exists an even integer. So I'm going to need to find some even integer, right? You can choose almost any even integer you want, right? But you'd have to be a little careful with what you choose, because, right, 4 isn't going to work, because I can't write 4 two different ways as the sum of two prime numbers. And it's like, okay, so I move on to 6. Can I do 6? So 6 can be 3 and 3, 4 and 2, 1 and 5. No, there's not two different ways of prime numbers there. So why don't I look at the number 10? Why don't I look at n equals 10? Okay, well, 5 plus 5 is equal to 10. So I just wrote it as the sum of two prime numbers. But 5 plus 5, that's the same thing as 3 plus 7. And those are two different prime numbers, right? So I just found an integer, an even integer, where I wrote it as the sum of two prime numbers two different ways, right? 5 plus 5 and 3 plus 7. That works. So I proved that there existed an even integer, okay? Now I will say 99.9% of the time in mathematics, okay? When it says prove there exists, that's great. We don't care what it is. We just want to prove it exists. Okay, so we happen to have found it this time, but we didn't really care what it was. Okay. All right. So that's one way to prove existential or proofs of existence. Okay. This is the constructive way, right? So we essentially, what we did is, we constructed the number and showed it worked, right? There's another way called non-constructive way, right? And the disadvantage to that is what I was saying before, where you don't know what it is, but you just kind of show it exists, right? But you don't know what it is, right? Unfortunately, this is the main way to prove things, but that's okay. We will get to those proofs much later because they're generally much harder, right? Like showing something exists and pulling out the example is great. Showing something exists, but not having what it is much more difficult, right? Because if I told you, I have a yellow paperclip on my desk, it exists, but I don't show you what it is, and I don't show you it, you'd have a little bit harder time believing me, right? You'd have to make sure like, okay, can you really reason to me that it's a yellow paperclip, right? Could you describe it to me where it is, right? So that's kind of how non-constructive proofs work. Okay, so now we're gonna do something else. We're gonna do disproving universal statements. Universal statements by counterexample. Okay. By counterexample. Okay, so let's think about this. A universal statement says for all something, right? So if I find just one counterexample, I have disproved the whole statement because it doesn't work for all of them. Okay, so that's what we're going to be doing. Okay, so let's do an example of this. So disprove the following. Okay, disprove the following. For all x and y in the real numbers, okay, any real number you can think of, if x squared equals y squared, then x equals y. I told you to disprove the following, so you know this is false. But sometimes it could just be like prove or disprove, right? So I want to disprove this, which means I need to think of two numbers where their squares are equal, but when I take the square root, they're not. Okay. So the easiest one for us to do would be like -1 and 1. Well, let's see. X squared equals 1 and y squared equals 1, which means that x squared equals y squared. Okay, I just had the if. Then x better equal y. They don't equal each other. So I just disproved it, right? Okay, I really wish I could ask for questions, but I can't. So if you have questions, email me, come to office hours, okay? I know this stuff is tricky at first, okay? All right, so that's great. Disproving, super nice, okay? Right, you say, okay, I have to think of one counterexample for disproving universal statements. I could do this. I can find one counterexample. Okay. Proving universal statements is a little harder. Okay. It's not that much harder. And there's universal statements. There's two ways to do it. Proving universal statements. Okay, so the first way is arbitrary, is what I call it. And you do this for all, if I say for all x and y in the real numbers, okay, it's arbitrary. Why? Because you can't literally check every single x and y in the real numbers. You can't check it. It's impossible, right? So the other way is through exhaustion. And that is checking every single possibility. It's not great. No one really does it this way, right? But it can be true. Okay, so let's try it. So let's do an example. So I'll do for all n in the integers. Okay, so for every integer, if n is even, and let's say n is between, the slide does 26. I think that seems a little silly, right? So let's do n is between 4 and 12. Okay, 4 and 12. N can be written as the sum of two prime numbers. Okay. The sum of two prime numbers. Okay. So let's do this. So I'm going to do the exhaustion way. Okay, which means I need to list every single even number between 4 and 12. And then I just show that I can write these even numbers as the sum of two prime numbers. Okay. 5, and what can 12 be written as? What can 12 be written as? 12 can be written as 5 plus 7. There it is. Okay. So I just checked every single even number between 4 and 12 and showed. I just literally showed, right? Every even number is written as the sum of prime numbers. Now, that's not great, right? Because as you can see, I just did even numbers between 4 and 12, and yeah, I had to check 5 things. But like, what if I wanted to show, you know, for every even number between 4 and 10,000? It's like, I don't want to check that many things. I don't want to check 5,000 things, right? So that's why, for the most part, we use arbitrary, or you could say general is also fine. Okay. Okay. So let's practice a proof. Let's practice a proof like that. Before I practice the proof like that, I'm going to show you something. Feel free to use it, you know, on your little cousins or your friends, or, you know, if you have kids, use it on your kids. So it's like a mathematical trick. Okay. So here's the trick. Okay. And this is an example of showing it works for every number. Okay. So this is an example of the arbitrary one. Okay. So you tell someone to pick a number. Pick a number. Okay. That's the first step. Okay. I'm going to leave space in between these, and we're going to come back and fill in like the proof. Okay. And then what you're going to do is you're going to tell them to add 5 to that number. Okay. And then what I want you to do is to tell them to multiply by 4. Okay. And then the next thing you're going to do is you're going to subtract 6. Okay. And then the next thing you're going to do is you're going to divide by 2. Okay. And then guess what? Their number is 7. Oh, sorry. Wait 1 second. You have to subtract twice the original number. Okay. And then that number is 7. And we're on step 7. Was that planned? I'm going to say it was. Okay. So you tell someone to pick a number. Okay. Let's say they pick some number. Let's say they pick some number X. You tell them to add 5 to that number. Now you have X plus 5. And then you say, hey, multiply that new number. I want you to multiply that by 4. Okay. So we'll get 4x plus 20. Then I want you to subtract 6. Okay, so now I have 4x plus 5 minus 6. So this is going to be 4x plus 14. Okay. And then what I want you to do is I want you to divide by 2. Okay, so if I divide by 2, I'm just going to do this. 4x plus 14 over 2. That's 2x plus 7. And then I want you to subtract twice the original number minus 2 times the original number. Well, look what I get. 7. No matter what number they pick, it will always be 7. So what we just proved, right, is we just showed, hey, for every number that someone picks, if you follow these steps, then you will get 7. Okay, this is an example of proving a general theorem, if you want to call it, right? So feel free to use this on your nephews, your kids, or whatever, right? You'll always get 7. Okay. Okay. So the way that we do it. So how do we do it? So how do we prove universal statements generally? Okay. How do we prove universal statements generally? Number 1. And this is what I'm going to say to do because I think it's beneficial when you're first starting to learn to write proofs. So number 1 is you're going to write it as like an if-then statement. Okay. So if-then statement. And why is this? Let me statement. And this is because then we can say, hey, for all x, remember this is universal statements. Okay, so for all x in my domain, if p of x, then q of x. Why do we do this? Because what we're going to do next, right, is you assume this. This is always going to be what you're going to assume. Always. Okay, so you assume the hypothesis to be true. Okay, always. And then the next step is you're going to show the conclusion is true. Okay. Through definitions, theorems, logic, whatever. Okay. So the reason I want you to do the first step is because oftentimes when you're stuck on writing a proof, it's because there was like an assumption you didn't make or a definition you're not using. So if you write out all your assumptions, you then go through your assumptions one by one and go, oh, what does the definition of this mean? What does the definition of this mean? What does the definition of this mean? Now I'm done. Okay. By writing all those out, you'll actually start building your conclusion. Okay. And you'll see what I mean when we do our example. Okay. So let's go ahead and do it. Example. Okay. Prove the sum of any 2 even integers is even. Okay. So here we go. This is our first one. This means for every even integer, no matter what it is, if I add 2 of them, they're going to be even. Okay. We can't actually check, right? Can't actually check all the even integers. It's not possible, right? So here we go. So I'm going to say if, or I'll say for all m and n even integers all right, let's just do it this way. Let's just say m and n. So you assume m and n are even integers. Okay? Assume m and n are even integers. Okay, I just made my assumption, right? I just made it. Now I write the definition. That's the next step. Okay? Thus, which means then, right? But people say thus. Thus, m is equal to 2k and n is equal to 2 times L. Doesn't matter, right? They're just variables. For k and L in the integers. That's what it means for m and n to be even. That m is 2 times some integer and n is equal to 2 times some other integer. Okay. Then, right, what does it say? The sum of any integers. So their sum, m plus n, is going to be equal to 2 times k plus 2 times L. Okay, which is fine. But look, they both have a 2 in common. So this is 2 times k plus L. Okay. And since k plus L is an integer, we know by definition of even integers, two times k plus L is even. Done. Right? You could put a little box at the end. You could put a little, I have a colleague who loves cats, so they put a little cat at the end of theirs, right? A box just means this is the end of proof, right? Okay. So look, I made my assumptions. I then wrote down the definition of my assumptions, and then I just started on my conclusion. I took the sum, and then I did some substitution, and then I pulled out a 2, and then we're done. Okay. Okay. So we could do another example here. Okay. And then, but what I want you to do is I'm going to write it, the theorem out. I want you then to pause the video. I then want you to do it, do the proof. Okay. And then unpause the video and double check to make sure we're writing the same thing. Okay. Let's do another example. Proof or prove for all integers R and S. Okay. If R is even and S is odd, then 3R plus 2S is even. Okay, that's what I want to show. Okay, so pause the video, try to do the proof. I'm going to start writing it. Or you can try to kind of follow along with me, whatever you want to do. Okay. So first thing, assumptions. Assume R is even and S is odd. Great. Okay, so now definitions. Thus, R is equal to 2k because it's even, and S is equal to 2m plus 1 for some K and M in my integers. Boom, definition done. Okay, now here we go. 3R plus 2S is going to be equal to 3 times 2K plus 2 times 2M plus 1. Okay. Make sure you can get to this step. Okay, make sure you can get to this step. So this is going to be equal to 6K plus 4M plus 2. Okay. Which is then equal to 2 times 3K plus 2M plus 1. Okay. So I say now, so 3K plus 2M plus 1 is equal, or not as equal, is an integer. So by definition of even integers, 2 times 3K plus 2M plus 1 is even. Done. Okay. So we just showed no matter what numbers you choose in the integers, 3 times it plus 2 times another number will always be even for all of them, right? We didn't have to check all of them. We proved it very generally. Okay. All right. So that's it for this video. Okay. That was kind of the introduction to proofs, right? We're going to do a lot more of it. Okay. And then I'll see everyone next time.